In 1971, two physicists, Haffaley and Keating, took some of the most precise devices humans had at the time, atomic clocks. They put them on commercial jets and flew them around the Earth, eastward and the westward. Another identical atomic clock stayed on the ground at the US Naval Observatory, acting as the home base clock. No magic, no extra tech, just let's move some clocks and see what happens. Einstein's theory of relativity had already made a hard prediction. Clocks in motion tick slower, and clocks deeper in a gravitational field tick slower. Not maybe, not in some cases. If his equations are right, then time itself must pass at different rates for different paths through the universe. Haffel and Keating were basically asking the universe, are you serious? And putting very expensive watches on the line. When the clocks came back and the data was analysed, the three clocks did not agree. The ones that flew came home offset from the one that stayed put by tens of nanoseconds. Tiny numbers, sure, but exactly the size and direction predicted by Einstein's equations. The eastward flight and the westward flight even had different shifts because their speeds relative to Earth's rotation were different. The result was not a vague hint, it was a match. Those flying clocks actually aged differently. They followed different routes through space-time and experienced different amounts of time. That is time travel, not the dramatic movie kind, but the real kind. Two objects once synchronized, forced by physics to disagree forever about how long the trip was. The universe does not care what your common sense says, it only cares about the equations. So once we know that motion and gravity literally change how fast time runs, the next question is obvious. What happens when we build an entire global navigation system on orbiting clocks that are all running wrong on purpose? Every time you open a Maps app, your phone listens to signals from the GPS satellites. Each satellite carries us atomic clocks and constantly broadcast timestamps. Your phone computes where you are by comparing those times and figuring out how long the signals took to reach you. That only works if you know exactly how fast those satellite clocks are ticking compared to clocks on Earth. Here's the problem. GPS satellites are far above Earth, where gravity is weaker. General relativity says weaker gravity makes clocks tick faster than clocks lower down. For GPS satellites, that adds about 45 microseconds per day compared to clocks on the ground. At the same time, those satellites are moving fast, several kilometers per second. Special relativity says high speed makes clocks tick slower. That subtracts about 7 microseconds per day. Add them up and the orbital clocks gain about 38 microseconds per day relative to Earth clocks. That sounds tiny, but light travels about 300 meters in a microsecond. After one day, if you ignore relativity, your position would be off by on the order of 10 kilometers. After a week, it's chaos. Your phone would tell you you're inside a lake. Planes would miss runways, shipping, banking, power grids, all of it would drift. So engineers do not ignore relativity. They pre-adjust the satellite clocks. They literally set them to tick at the wrong rate on the ground so that once they're in orbit, with weaker gravity and high speed, they tick at the right rate relative to Earth. If they didn't, GPS would fail, not be a bit worse. Fail. The fact that your blue dot sits nicely on the road is permanent, daily proof that time runs differently in different places. We've now hit something important. Your location on Earth is only accurate because we accept that time is not universal. Time depends on where you are and how you move. That's not philosophy, that's your commute. But maybe you still think, fine, clocks and satellites, that's technology being weird. So let's strip the technology away and look at what the universe is doing with raw particles hitting Earth right now. Because high above your head, something even more disturbing is happening. Cosmic rays, high-energy particles, from space slam into the upper atmosphere and create muons, unstable particles similar to heavy electrons. A muon's mean lifetime at rest is about 2.2 microseconds. That is how long on average it exists before it decays into other particles. If you do a simple calculation with normal non-relativistic thinking, there is a problem. Even if muons move close to the speed of light, 2.2 microseconds is not enough time for them to travel from the upper atmosphere down to sea level. They should decay long before they get anywhere near you. But when we actually measure what hits the ground, we find a strong muon flux at sea level. Roughly 1 muon per square centimetre per minute passes through the ground, through detectors, through you. They are clearly surviving the trip. Classical pre-relativity physics says they should be gone. Reality says they arrive in huge numbers anyway. Relativity explains this exactly. From our point of view on Earth, the muons are moving so fast that their internal clocks are slowed down. Their lifetime timer runs more slowly than ours. Instead of 2.2 microseconds of survival in our frame, they get more time, enough to cross the entire atmosphere before decaying. From the muon's point of view, its lifetime is still 2.2 microseconds, but the distance it has to travel is shorter because space in the direction of motion is contracted. 2 viewpoints. 1. Law of physics. The important part is not the math detail. The important part is the verdict. The only reason those muons exist at sea level is because time for them is not the same as time for you. Their path through space-time is bent so that they should be dead becomes they arrive alive. That's not a small correction. That is the universe openly violating everyday intuition. Put all this together. Clocks on planes come home disagreeing. Clocks in orbit must be corrected so your navigation doesn't fail. Particles created high above your head live long enough to reach you only because their time is stretched. This is not a special effect. This is the normal operation of reality. So here is the hard line. You are already a time traveller, whether you like that idea or not. Your body is sitting in a gravitational field, so your time runs slightly slower than someone far out in empty space. The top of your head is aging a tiny bit faster than the soles of your feet. As you move, even at everyday speeds, your personal time diverges by microscopic amounts from someone sitting still. The satellites above you, the airplane you flew in last year, the muons passing through your chest, all of them are aging at their own rates. Forward time travel is not optional. It is built into the structure of space-time and baked into the technology that runs modern civilization. We do not get to vote on it. We can only measure it and use it. And here's the unsettling part. Everything we just talked about is the small version. Tiny differences, nanoseconds and microseconds, but the same laws that quietly bend time on planes and satellites can, in more extreme situations, stretch time until the gap is not microseconds but years, decades, centuries. If the universe lets us do that in small doses, what happens when we push it to the limit? How far can you actually step into the future? And more disturbing, does that future already exist? Waiting for you, sitting somewhere in the structure of space-time right now? What if every moment of your life, of your birth, this exact second, your death is already there in the universe, laid out from start to finish and you're just sliding through it, unable to jump tracks? Not as destiny talk, but as a cold statement about how space-time might actually be built. That's the block universe idea. And if it's even approximately right, then your future isn't something that appears later. It's a location. Einstein's relativity doesn't treat space and time as separate things you can pull apart like Lego pieces. It treats them as space-time, one 4-dimensional structure. 3 dimensions of space, 1 of time, fused into a single geometric object. In that picture, anything that happens, a supernova, you blinking, a satellite sending a signal, is an event. A point in this 4-dimensional structure. You don't have a moving present in this view. You have a world line. That's the curve your existence traces through space-time, where you are and when you are, all in one line. Right now you feel like you're living in a single moving moment. But in the math, your birth, this second, and your last heartbeat are all points along that world line. The theory doesn't single out now as special. It just says, here is the entire track. Physicists sometimes call this the block universe, not because they're trying to be poetic, but because the equations treat the whole history, past and future, as one fixed 4-dimensional object. You don't see it that way because your brain is a little biological machine that only experiences one slice at a time. Here's the brutal implication. If the block picture is how reality works, then your future already has coordinates. It's not made later. It's part of the same structure as your past. You just haven't reached those coordinates along your world line yet. So, why does the universe force us into this uncomfortable picture? Why can't we just go back to a simple time flows, everything else sits there model? The answer is, the speed of light leaves us no choice. You don't get to pick the speed of light. The universe does. That number c is about 300,000 kilometers per second in vacuum. More importantly, experiment after experiment says the same thing. You cannot find a frame of reference where light is going any other speed. No matter how you're moving, when you measure light in vacuum, you get the same c. We've checked this with particle accelerators, where beams circulate close to light speed. We've checked it with radio signals bouncing between antennas and satellites. We've checked it with timing of pulsars, gamma ray bursts and gravitational waves. The result is always the same. C is invariant. If C is fixed, something else has to give. That something is your naive idea of space and time. To keep C the same for everyone, distances and durations have to warp. That's why moving clocks slow down. That's why rulers shrink along the direction of motion. That's why those airplane clocks and cosmic muons behave wrong compared to everyday expectations. The equations of relativity are not built from the assumption time is universal. They are built from C is universal. Space and time are forced to twist to protect that rule. Once you accept that, you're automatically pushed toward the space-time block universe view. Time becomes a dimension that gets mixed with space depending on how you move. So here's the next knife twist. If space and time are this flexible, what happens to the idea of a single shared now? In everyday language, we talk like there is one present moment that stretches across the whole universe. You and a galaxy a billion light years away are both existing right now. That sounds obvious. Relativity says it's wrong. In Einstein's theory, simultaneity is relative. What counts as at the same time depends on how you're moving. Two observers, moving differently, can look at the same two events and disagree about which one happened first, or whether they were simultaneous, without either being wrong. This is not just abstract talk. All the experiments we mentioned hammer this home. The planes in the Hafele-Keating experiment followed different motion, and their now surfaces through space-time don't line up with the ground clocks now. GPS satellites have their own slices of simultaneity, slightly tilted relative to ours on the surface. Muon decay curves match the prediction that time along the muon's path is not the same as time along Earth's. When you combine all of this, the picture is clear. There is no universal this moment everywhere built into physics. The universe does not provide one global ticking clock that all events share. It gives each observer their own way of slicing space-time into past, present, future. That's a direct hit on the classical view of time as one, flowing river carrying everything along together. In the relativistic view, different observers carve up the block in different ways. Your now is not the universe's now. There is no such thing. So if there's no universal now, and if space-time looks like one big four-dimensional structure, you're forced toward a disturbing question. If the block is real, is time travel basically just navigation? In a block universe picture, all events exist in the same sense. The dinosaur extinction event, the first human for your next birthday, the last red dwarf star going dark trillions of years from now. They're all points in space-time. When you move into the future, you're not creating it. You're reaching a part of the block that was always there. Then what would it mean to travel in time? It wouldn't mean rewriting the block. That would be like trying to rewrite the coordinates of a map that is already printed. Instead, it would mean finding a path through the block that loops in a strange way. A path where your world line curves around and intersects its own past. General relativity actually allows paths like that. They're called closed timelike curves. Timelike means you're always moving slower than light, like normal matter. Closed means you eventually come back to where and when you started. In some of Einstein's equations, these loops just appear. No cheating with faster than light travel, just weird geometry. Then there are wormholes, tunnels through space-time that in theory could connect different locations and different times. If you had two ends of a wormhole and you made them age differently, by moving one fast or parking one in strong gravity, you could, on paper, walk in one mouth and walk out at an earlier external time. Here's the important point for this video. These ideas are not stapled onto some wild new theory. They drop out of the same general relativity that explains GPS, black holes, and gravitational waves. The same framework that keeps passing experimental tests keeps quietly whispering, by the way, in some configurations time loops show up. That doesn't mean the universe actually uses those configurations. It doesn't mean wormholes or closed timelike curves exist in reality. But it means this. If space-time really is a block, and if general relativity is even approximately right about its geometry, then time travel is not about breaking the rules. It's about riding the rules to their extreme. You're already moving through the block along one boring, almost straight world line. The terrifying question is whether physics will ever let you bend that line into something much stranger. What if the thing you call gravity isn't really a pull at all, but a glitch in time itself, changing how fast your seconds tick just because you're near something heavy? Once you accept that space-time is real, you can't keep gravity as a simple force. You have to accept something harsher. Massive objects are messing with the rate at which the universe lets you move into tomorrow. Einstein's general relativity makes a blunt claim. Gravity is curved space-time, so put mass and energy somewhere and space-time bends. Once space-time bends, the natural paths through it, the paths that free-falling objects follow, curve. You see an apple fall? The math says the apple is following the straightest possible path in a warped four-dimensional landscape. Here's the part that ties directly to time travel. When space-time curves, time itself changes speed. Clocks deeper in a gravitational well run slower than clocks higher up. Closer to Earth's centre, your seconds stretch a little. Higher up in the field, your seconds are shorter. This isn't theory floating in a vacuum, it's measured. We've put atomic clocks at different heights in Earth's gravity and watched them drift apart. One clock in a basement, another on the roof of the same building wait, then compare. The higher clock, in slightly weaker gravity, ticks. Zoom out. GPS satellites again. Their clocks, higher up in weaker gravity, run faster than ground clocks, and we're forced to correct for that just to keep navigation working. So gravity is not just about objects falling, it is literally about time running at different rates in different places. The deeper you go into a gravitational well, the more your time is slowed relative to someone far away. You don't feel it a beat, but the equations don't care. They say mass slows time, period. But if Earth's gravity already changes time by measurable amounts, what happens when you take that idea to the most extreme objects the universe allows? Near a black hole, the rules you've seen on planes and in satellite systems get amplified. A black hole is a region where space-time is curved so strongly that past a boundary called the event horizon, nothing can come back out. Not light, not signals, nothing. The important part for time is what happens as you get close to that horizon. From far away, if you watch an object fall toward the event horizon, you never see it cross. You see its signals get slower, weaker. Its clock appears to tick more and more slowly. In the limit, as it approaches the horizon, it seems to freeze, not because it actually stops, but because the time on its path through space-time is being shredded relative to yours. General relativity predicts this. Extreme gravitational time dilation. Time for the falling object keeps going normally in its own frame. But Compared to a distant observer, its progress toward the horizon is dragged out toward infinity. Time and space get mixed so strongly that before and after near the horizon stop lining up with your intuition. We don't just trust the equations. When LIGO first detected gravitational waves, tiny ripples in space-time, from colliding black holes, in an event called GW150914, it was recording exactly this kind of extreme gravity in action. Two black holes, each dozens of times the mass of the Sun, spiraled in and merged more than 1 billion light-years away. The signal we picked up on Earth was space-time itself, stretching and squeezing. Now, look at the numbers. In GW150914, roughly 3 times the mass of the Sun was converted directly into gravitational wave energy in a fraction of a second. Not burned as fuel, not radiated over billions of years, just gone. Turned into a burst of space-time distortion that raced across the universe at light speed. For a brief moment, that system outshone all the stars in the observable universe in gravitational wave power. That is space-time getting hit so hard that calling it curved feels too soft. When that kind of mass energy is moving and merging, time is not just gently bent, it is stretched and twisted. The same laws that tweak nanoseconds on airplanes are responsible for these cosmic-level distortions. So here's the key move. If gravity changes the rate of time, and black holes crank that effect up to extremes, can you use gravity as a time machine? For forward time travel, the answer is yes. Imagine you have a ship that can orbit just outside the event horizon of a supermassive black hole. You never cross the horizon, so you're still able, in principle, to leave. But you're deep in the gravitational well, where time runs very slowly compared to the rest of the universe. You and your crew orbit close in for a few hours according to your onboard clocks. But when you climb back out and return to some faraway region where gravity is weaker, you discover that years have passed for the outside universe. Maybe decades, maybe more, depending on how close you got and how long you stayed. From your point of view, you just did a short mission. From the universe's point of view, you jumped into the future. That is forward time travel by gravity. No new theory, no sci-fi hack. It's the same time dilation we correct for in GPS, amplified by orders of magnitude around extreme masses. This creates a one-way ticket effect. You can move forward into someone else's future faster than they do by spending time in regions of strong gravity, or by moving at speeds close to light. If we had the engineering to safely orbit near a black hole, we could send people on future jumps. The catch is simple and brutal, coming back to your original. When is not on the menu. Gravity-based time travel, as we understand it, only lets you overshoot everyone else into their future. You can leave 2100, come back when the universe is in 2300, having only experienced a small fraction of that time yourself. But there is no known way to then turn around and go back to 2100. So the gravity is already a time machine, and black holes are its most extreme version. If you sit near something massive enough, your personal time can decouple violently from the rest of civilization. The laws are not the problem. The only things stopping us are engineering, distance, and survival. And that pushes us into the next, more dangerous question. If gravity and motion let you jump forward, what kind of space-time tricks would it take to bend your path all the way around, back into your own past? What if I told you there is one time travel trick that does not need black holes, wormholes, or alien technology, just a fast enough rocket and a long enough trip? And it is 100% allowed by the laws of physics we already use. No loopholes, no new theories. You go, you come back. The calendar on Earth says future, while your body says not that much time passed. That is not sci-fi, that is special relativity. Here's the core rule: the faster you move compared to Earth, the slower your proper time runs. Proper time is the time along your own path through space-time, the time your heart feels, your watch measures, your brain experiences. Stay on Earth and your proper time matches Earth time. Get in a rocket, accelerate to a speed close to the speed of light, cruise for a while and then come back. When you land, your clock will show less time passed than clocks on Earth. This is the famous twin power twin paradox, stripped of drama. One twin stays home, one twin goes on a high-speed round trip. When the travelling twin returns, they are younger. Not just look younger, their cells have literally experienced less time. Their chemistry, their biology, all of it has run slower compared to their siblings' timeline. Special relativity doesn't treat this as a weird exception. It demands it. The formula that links your speed to your time is locked in. As your speed gets close to c, the speed of light, the factor that slows your time, physicists call it gamma, grows larger. At 0.9 c, your time is already running noticeably slower than Earth's. Push closer to 0.99 c and the effect becomes brutal. A few years for you can line up with decades for people who stayed home. So yes, go fast and come back younger actually works in principle. If you can build a rocket that can safely accelerate you to a significant fraction of light speed, and if you can survive the trip, you have a direct, boring, engineering-style way to jump into the future. Not metaphorically, when you step off the ship, the world is older than you are supposed to be if you'd stayed. That raises a hard question. Has anyone already done a tiny version of this in real life, with real humans, not just in thought experiments? We basically have. Look at astronauts. Astronauts on the International Space Station are orbiting Earth at about 7.7 kilometers per second. That's nowhere near light speed, but it's fast enough that special relativity applies. Their motion makes their time run slightly slower. At the same time, they're higher up in weaker gravity, which makes their time run slightly faster. You have to combine both effects. When NASA studied twin astronauts Scott and Mark Kelly, the setup was simple. Mark stayed on Earth. Scott spent almost a year in orbit. When Scott came back, precise measurements showed he had aged a tiny bit less than Mark, by milliseconds, due to relativistic effects. Not minutes, not hours, milliseconds. But they're real, measurable, and exactly what the equations of relativity predict. That is a human-scale, small, but genuine version of the twin paradox. One brother's world line through space-time was bent by high-speed orbit. The other's was not. The difference in time is tiny because our rockets are slow compared to light and the mission length is short. But the direction of the effect is clear. Go fast, experience less time. If we had the technology to push astronauts to a much higher fraction of light speed and let them cruise for years, the gap wouldn't be milliseconds. It would be years, maybe decades. The physics does not flinch when you scale it up, only our engineering does. But humans are not the only test subjects. We already run extreme time travel experiments every day in machines buried underground. So what happens when we stop talking about rockets and start talking about particle accelerators? In particle accelerators, we routinely take unstable particles, like muons, and fire them around rings at speeds extremely close to the speed of light. At rest, a muon's mean lifetime is about 2.2 microseconds. That's how long, on average, it exists before decaying. But when we accelerate muons to high gamma factors, their lifetimes in the lab frame stretch dramatically. They don't decay in 2.2 microseconds of lab time. They last 10 times longer, 100 times longer. The exact factor matches the time dilation predicted by special relativity. This is not a vague trend. It's a clean, precise match. Lifetime multiplied by gamma. The faster they go, the larger gamma gets. The longer they live from our point of view. The particles are not magically more stod. Their internal processes are simply running in slower time compared to us. In other words, we have already pushed subatomic particles into the future by extending their lifetimes far beyond what you would expect if time were absolute. We create them, accelerate them, and watch them persist for many, many natural lifetimes as seen in our lab clocks. That is forward time travel on a microscopic scale, happening constantly in facilities around the planet. So if speed gives you control over how quickly you move into the future, why not push it harder? Why not just accelerate yourself past the speed of light and argue that you've somehow outpaced cause and effect and slipped into the past? This is where the fantasy dies. As your speed increases, the energy required to keep accelerating you doesn't grow linearly. It explodes. The relativistic energy of a moving object is tied to that gamma factor. At low speeds, gamma is close to 1 and you're in the normal Newtonian world. As your speed approaches c, gamma shoots upward. To get closer and closer to c, you have to pump in more and more energy for smaller and smaller gains in speed. In the equations, as your speed approaches c, gamma tends to infinity. That means the energy required to reach the speed of light itself is infinite, not huge, not impractical. Infinite? A spaceship with any non-zero rest mass cannot be accelerated to light speed under standard relativity. It doesn't matter how advanced your technology is, you hit a wall built into space-time. Going faster than light is even worse. At superluminal speeds, the math of special relativity stops describing sensible time-like paths. You break the basic structure that keeps cause before effect. You get violations of causality, events that can look like an effect coming before cause in some frames. The theory does not say, sure, go ahead and do that. It says, those trajectories are not allowed for objects with mass, so you cannot just gun it, outrun light, swing around and come back into your own past. The time travel that speed gives you is strictly one-directional. You always end up in someone else's future, never behind your own starting point. To move backward in time, to challenge causality itself, you need something more extreme than going fast. You need space-time itself to be arranged in a weird way. Wormholes, closed time-like curves, warped regions that general relativity admits on paper, but that reality might refuse to build. The rocket trick is real, it's cold, it's already measured in small doses, and it scales up in a way that should make you nervous. We already know how to leave people behind in time, we just don't know how far we dare push it. What if I told you we could already build a real twin paradox, not on a chalkboard, but using the hardware we have right now, and the only reason we haven't pushed it to the limit is money and fear, not physics. One twin on Earth, one twin locked into orbit for decades. When then they reunite, the difference in their ages is small, but it's real. One of them literally lived less time in the same universe. Take the ISS. It's not just a lab, it's already a crude time machine. The station orbits Earth at about 7.7 kilometers per second. That speed means special relativity is in play. Motion slows your proper time. At the same time, being higher up in weaker gravity speeds your time up a bit. Add those two effects and you get a tiny net time difference compared to someone on the ground. Now, stretch that idea. Imagine we deliberately keep an astronaut in low Earth orbit not for 6 months, not for a year, but for multiple decades. Rotations, crew swaps, doesn't matter. You keep the same person in that relativistic environment as much as humanly possible. Their twin stays on Earth the whole time. You run this experiment for 30-40 years. Relativity says the orbital twin will age slightly less. Not by years, not by months, but by measurable amounts. Milliseconds building into tens or hundreds of milliseconds, maybe creeping toward fractions of a second. If you integrate over enough time and enough missions, you'd need very precise atomic clocks and careful bookkeeping, but you would eventually end with two genetically identical humans whose bodies have experienced slightly different amounts of time because one spent a life riding Earth's gravity and rotation differently. It's not dramatic enough for a movie. No one steps off the capsule to find flying cars and ruined cities, but it proves a point. Even with slow, low-orbit flight, you can cheat time a little. The ISS is already a weak time machine. We just don't lean on it hard enough for it to hurt. So here's the next step. What happens if we stop thinking space station and start thinking starship? Forget 7.7 kilometers per second. Start talking about ships that cruise at 0.9 C, 0.95 C, 0.99 C, 90%, 95%, 99% of light speed. At these speeds, the time dilation factor gamma explodes. At around 0.99 cents, gamma is roughly 7. That means for every 1 year that passes on board your ship, about 7 years pass back on Earth. Run the numbers. You build a relativistic starship. You accelerate up to 0.99 C, cruise for a while, turn around, come back and decelerate. From your point of view, you spend 20 years of your life on this mission. That's a long career, but it's still your lifetime scale. When you return to Earth, more than 140 years have passed there. Everyone you knew is dead. Languages have drifted. Technology might be unrecognizable. You did not jump through a portal. You just took a very fast trip along a timelike path that general relativity fully allows. But the result is the same punch in the gut. You walked out of your own century and into someone else's. This is forward time travel you can write into an engineering spec. Cruise speed, 0.99 C. Mission time, ship frame, 20 years, elapsed time, Earth frame, 140 plus years. You don't need poetry, you need delta V and shielding. Use 0.9 cents instead of 0.99 cents, and the effect is weaker but still huge. Gamma is a bit over 2. 1 year for you is a bit over 2 years for Earth. Do that long enough and you still divorce your personal timeline from the home planets. The curve of your world line through space-time leans harder into the time axis than theirs. You survive longer into the universe's future than any stay-at-home human could, simply because you took the fast route. So, what actually stops us from doing this? The equations don't. They are fine with it. The barrier is not theoretical physics. The barrier is flesh, bone, and fuel. First problem, acceleration. You can't just slam humans from 0 to 0.99 C like flipping a switch. Sustained high acceleration crushes the body. We know humans can survive around 1g, Earth gravity, for long periods. Higher g-forces are possible for short bursts, but not for years. So you're limited in how quickly you can ramp up and ramp down. That stretches out the mission profile and raises fuel demands. Second problem, radiation. The faster you go, the nastier the universe becomes. Interstellar space isn't empty. It's full of dust, gas, and high-energy particles. At 0.99 C, even tiny grains hit like bullets. Cosmic rays slam into your ship with insane energies. You're basically flying into a storm of radiation that wants to tear DNA apart and punch through electronics. You need absurd shielding or clever magnetic fields to survive without turning the crew into cancer statistics. Third problem, energy and fuel. Reaching 0.99 C with anything bigger than a pebble demands insane amounts of energy. Chemical rockets are a joke at this scale. You're talking about fusion antimatter, or something equally violent just to get a reasonable mass fraction to relativistic speeds. And then you have to slow down again without frying everyone. So yes, the engineering is a nightmare. The rocket equations are cruel, the biology is fragile, but pay attention to what's missing from that list. Physics says no. It doesn't. Physics says, bring enough fuel, enough shielding, and enough patience, and you can do this. Relativity is totally relaxed about you jumping far into the future by coasting through space-time on a fast ship. You don't break causality. You don't need exotic matter. You don't need new laws. You just need a terrifyingly capable space program. Put that together with gravity-based time dilation in massive objects, and the verdict is not ambiguous. We already live in a universe where speed and gravity let you leap ahead of everybody else's clock. Keep someone in orbit for decades and they cheat time by fractions of a second. Send someone on a near light speed cruise and they cheat time by decades or centuries. Or park someone near a black hole and let them orbit safely, and their personal hours could match years or more for the outside universe. So this big question is no longer, is forward time travel possible? That one is done. It's baked into the structure of space-time. The real question, the one that actually threatens causality and logic, is this. If you can already move into the future faster than everyone else, is there any way, any geometry, any trick, any exotic structure that lets you come back to before you left? Here is where the equations stop being polite and start getting dangerous. General relativity allows tunnels in time, not as a metaphor, as an actual solution to the field equations. Two distant regions joined by a finite path that is shorter than going the long way through normal space. That structure has a name, a wormhole. In the original work by Einstein and Rosen, you get what's now called an Einstein-Rosen bridge. It connects two regions of space-time on paper, but that bridge pinches off too fast for anything to cross. It's a one-moment connection, not a usable passage. Still, once that door is open mathematically, people ask the next question. Can you tweak the setup so the tunnel stays open long enough for something or someone to go through? Later work showed that general relativity is flexible enough to allow traversable wormholes in principle. You write down a space-time metric with two mouths, a throat connecting them, and a geometry that lets signals, objects, or travellers go in one side and come out the other without hitting a singularity. The math does not scream impossible. It says, fine, but you're going to pay a price. Now here is the time travel part. Imagine you somehow have such a traversable wormhole with two mouths, mouth A and mouth B. At first they sit near each other and are synchronized in time. Then you take mouth B on a trip. You accelerate it to high speed or park it deep in a strong gravitational field, then bring it back. You already know what that does. Time dilation. Mouth B ages less than mouth A. You reconnect them in space. From the outside universe's point of view, the clocks at A and B no longer agree, as maybe a year has passed for a while, only a month passed for B. But from the inside of the wormhole, the geometry still ties them together as if they share a common internal time. Now, walk through, step into mouth B, where the local external time is later, traverse the throat, and step out of mouth A, which is now at an earlier external time. You have moved along a smooth path, never going faster than light locally, and yet you have exited into your own past according to the larger universe. In plain terms, use a wormhole, move one mouth into a different temporal position via relativity, bring it back, and you have built a time machine. That is not fan fiction. That is straight from the logic of GR plus time dilation. If traversable wormholes exist and can be manipulated, time travel is a side effect, not an add-on. So why are we not already doing this? Because the bill is brutal. To keep a wormhole throat open, the curvature of space-time in that region has to be supported by matter or fields that violate the usual energy conditions. The stress-energy tensor has to do things normal matter refuses to do. In simple language, you need exotic matter with negative energy density as seen by some observers. Negative energy density is not just less than usual. It is literally energy with the opposite sign. If you had a box full of it and added it to a system, the total energy would go down. Classical matter does not behave like this. Rocks, gas, dust, all have positive energy density. Quantum field theory does allow small temporary negative energy densities in certain setups. The classic example is the Casimir effect. Place two conducting plates very close together, and the quantum vacuum modes between them differ from the outside. That difference shows up as a tiny attractive force, which you can describe as a region with effectively lower than normal energy density. But that is a fragile tiny effect on microscopic scales. It is not a stable slab of negative energy that you can shape into a ring, weld around a wormhole throat, and turn into a highway. Every serious attempt to design a traversable wormhole geometry hits the same obstacle. You need a huge amount of exotic matter arranged in a controlled, long-lived structure. Our current physics does not provide any way to do that. The quantum effects we know are weak, noisy, and tightly constrained. So on paper, wormholes look clean. In practice, the material requirements look insane. That gap between solvable equations and buildable structure is where the whole idea currently sits. Meanwhile, the universe is giving us new ways to hunt for anything this exotic actually existing out there. Gravitational wave detectors like LIGO and Virgo record ripples in space-time from compact object mergers. Most signals match standard black hole or neutron star collisions very well, but some events have odd features. One famous example is GW 190521, a short, heavy signal that looks more like a sharp burst than a clean chirp with a long spiral. Most analyses show it is still consistent with a merger of two very massive black holes that spend less time in the detector band before colliding. But some researchers have asked a dangerous question. Could signals like this be hinting at more exotic objects? Boson stars, exotic compact objects, even wormhole-like structures with different ring-down behaviour. This is speculative. It is not the consensus. Standard black hole models fit the data better and with fewer assumptions. But the important part is that physicists now use gravitational wave data as a direct probe of strong-field gravity. They are willing to test wild ideas against real signals and see what survives. Exotic horizons, echo signals, non-standard mergers, all of these get pushed through the machinery. So far, nothing screams wormhole in the data. No clear, repeated echoes that can't be explained. No waveforms that require a tunnel instead of a hole. Just a few weird events that keep theorists busy. Strip it down to the observational verdict. We have 0 confirmed wormholes, none in the sky, none in labs, no object we can point to and say that is a tunnel in space-time. What we do have is a theory, general relativity, that allows wormhole-like solutions under extreme conditions, plus quantum field theory that allows tiny negative energy effects, plus ever-improving experiments that constrain how much weirdness we can hide in the universe. Right now, wormholes sit in a very specific box. Allowed by some versions of our equations, blocked by everything we know about actual matter, not yet seen in the wild. They could exist in principle. They might be absolutely forbidden once we have a full theory of quantum gravity. We just don't know yet. But from a time travel perspective, they matter for one reason. They are our cleanest mathematical route to two-way time travel. Forward and backward. Leave, come back to before you left. If traversable wormholes are real and controllable, then building a time machine is a matter of extreme engineering, not breaking physics. If they are impossible, then the universe has quietly shut down one of the most direct paths to time tourism. But general relativity still isn't done causing trouble. Even without wormholes, the equations admit entire space-times where time loops on itself and lets you walk into your own past. So the question turns darker. Even if tunnels are off the table, does the geometry of the universe itself allow you to live on a path that closes back around in time? There are solutions to Einstein's equations where you can walk in what feels like a normal path, never exceed the speed of light, and still arrive in your own past. No warp bubbles, no portals, just space-time curved so violently that later loops back into earlier. Once you've seen that in the math, you don't unsee it. Kurt Gödel, the same Gödel famous for those brutal incompleteness theorems in math, took Einstein's general relativity and asked a nasty question. What if the entire universe were rotating? Not stars orbiting in galaxies, but the whole cosmic fabric spinning on a large scale. He found a solution, a rotating universe where space-time is twisted enough that closed timelike curves exist. Closed timelike curves, or CTCS, are paths through space-time that are timelike, meaning you move slower than light the whole way, like normal matter, but they loop back to where they started. Follow one of those paths and you end up in your own past, still obeying no faster than light. You don't cheat the speed limit, you cheat the structure of time itself. Gödel's rotating universe is mathematically valid. It satisfies Einstein's equations. It's internally consistent. The equations do not reject it. In Gödel's cosmos, you could in principle launch a spaceship on the right trajectory and, after a long enough journey, intersect your own earlier world line. You could meet a younger version of yourself without ever breaking relativity's rules about speed. So, why isn't this a how-to guide instead of a warning sign? Because our universe does not look like Gödel's. We don't see evidence for a global rotation of space-time. Observations of the cosmic microwave background, the large-scale structure of galaxies, and the overall symmetry of the universe point to something very close to non-rotating on cosmic scales. The real cosmos looks boringly isotropic and homogeneous, not twisted like Gödel's model. Ding! Still, the fact remains. Our best gravity theory calmly admits a whole universe where time loops are built in. It had to be killed not by the equations, but by data. That's the pattern you need to keep in your head. If you think, fine, that's a weird toy universe, not ours, the next question is obvious. Can you get closed time-like curves in more local setups, something like a machine or an object instead of the entire universe? General relativity says yes again. One famous idea is the Tipler cylinder. Imagine an infinitely long, extremely dense cylinder that spins incredibly fast around its long axis. The rotation drags space-time around with it. In the right configuration, the geometry around this spinning cylinder can contain closed time-like curves. A spaceship following certain paths around it, always slower than light locally, could loop back into its own past. The problem jumps out immediately. Infinite cylinder. You don't get to build that. When people tried to see if a finite, more realistic cylinder could do the same thing, the conditions got messy and far less promising. The clean time machine setup depends on an object that does not exist in our universe and cannot be built. Then you look at spinning black holes. Black holes. These are solutions of general relativity where the black hole has angular momentum. The geometry inside them is more complicated than in the non-spinning Schwarzschild case. In some regions deep inside a Kerr black hole, the math says closed time-like curves appear. Time and space swap roles in bizarre ways near the ring singularity. On paper, it's simple. Go inside a spinning black hole, navigate the region with CTCs, follow a time-like path, and you might come out in your own past. In reality, this is basically the universe saying, Sam, you can have your time loops, but you have to earn them by diving into a lethal gravity blender beyond an event horizon. Tidal forces, instabilities, and the fact you can't send signals back out once you're behind the horizon all team up to make this more of a death sentence than a time machine. The geometry might allow closed time-like curves. The actual physical conditions make them useless to any observer who wants to report back. So you get a pattern. Gödel's rotating universe, Tipler cylinders, deep Kerr interiors. All of them produce closed time-like curves in principle, but they all come with absurd baggage. Unrealistic global rotation, infinite objects, or regions hidden behind horizons that kill you and trap you forever. This is where Stephen Hawking stepped in with a more global suspicion. Maybe the universe itself refuses to let time machines fully form. He called this the chronology protection conjecture. The slogan version is simple: the universe hates paradoxes. The idea is that whenever you try to create conditions that would allow closed time-like curves in a realistic way, say by manipulating wormholes or arranging extreme gravitational fields, quantum effects might go berserk near the would-be time loop region. Quantum field theory in curved spacetime says that vacuum fluctuations, the jitter of quantum fields even in empty space, can be amplified by strong gravity and weird causal structure. In many calculations, when you try to build a spacetime with a region of CTCs that forms from normal initial conditions, the stress energy of quantum fields near the boundary of that region tends to blow up. You get infinite, or at least huge energy densities, enormous pressures, a kind of quantum back reaction that can distort or destroy the geometry you were trying to use as a time machine. In plain language, As you push space-time toward forming a loop in time, the quantum fields that live in that space-time start screaming. They dump so much energy into the region that the geometry you wanted gets torn apart or prevented from forming in the first place. The universe protects its chronology by letting quantum mechanics set the time machine on fire. Do we have a full proof of chronology protection? No. We don't have a complete theory of quantum gravity, and the calculations we do have are often in simplified models. But the trend is suggestive. Many attempts to get clean, buildable time machines and semi-classical gravity run into this wall of divergences and instabilities. So where does that leave us? On one hand, our best classical theory of gravity, general relativity, openly allows solutions with closed timelike curves, entire universes where time travel is baked in, exotic objects and setups where, under the right conditions, you can follow a path that returns you to your own past without breaking the speed of light. On the other hand, our actual universe does not look like Gödel's rotating solution. We do not see infinite rotating cylinders. The interior of spinning black holes is cut off from us by horizons and lethal physics. Every time we try to get realistic with time loops, quantum effects seem to rise up and threaten to wreck the space-time. So time travel to the past is not ruled out by the basic math. It's not forbidden by general relativity as a whole. It is probably ruled out, or at least heavily suppressed, by a mixture of initial conditions. The universe started in a state that doesn't allow this, and quantum tantrums that punish any attempt to force causality into a loop. That's the tension you're stuck with. The equations are more permissive than the universe seems to be. And this is all before you fully bring in quantum mechanics itself, with entanglement measurement and all the strange correlations that already bend your sense of cause and effect even without loops in time. If classical space-time geometry alone already walks along the edge of paradox, what happens when the weirdest part of physics starts playing in that arena too? People love to say quantum mechanics means anything is possible. No, it doesn't. It means reality is colder and more alien than your common sense, but it still has rules. And when it comes to time travel, quantum theory gives you zero mercy. It gives you strange correlations and not magical messages from the future. Start with entanglement. Two particles are created in a joint quantum state. Measure one here, measure the other far away, and their results are correlated in a way no classical hidden variable model can explain. Bell tests have hammered this again and again. The correlations are real, they violate classical bounds, and they don't care about distance. This is where people immediately jump to, so can I send a signal faster than light? Can I send a bit of information into my own past? The answer, tested over and over, is no. You cannot use entanglement to send a controlled message. You can't choose the outcome of your measurement. You can only choose what you measure, and the local results look random until you compare notes with the other side using normal, slower-than-light communication. Every experiment so far respects no faster-than-light signalling. The statistics of measurements on one side cannot be influenced in a way that carries usable information by what you do on the other side. The correlations snap into focus only when you bring the data together later. That's not a time machine. That's a weird non-local structure glued on top of a causal backbone that still respects light cones. So entanglement is not the channel you use to email next Thursday from last Monday. It's spooky, but it's not a hotline to your own past. Then come the delayed choice and quantum eraser experiments, the ones that get abused in clickbait headlines. You've probably heard the line, "We changed the past by deciding how to measure a photon after it went through the slits." That sounds like time travel, it's not. Here's the rough idea. You send a photon toward a double slit. In a normal double slit experiment, if you don't mark which slit it went through, you get an interference pattern, wave-like behavior. If you do mark which path it took, the interference disappears, you get particle-like behavior. Now, in a delayed choice version, you make the decision about whether to keep or erase the which path information after the photon has passed the slits, but before you detect it. When you look at the data, it seems like your later choice determines whether the photon was a wave or was a particle earlier. That's where people jump to retro-causality and we change the past. Standard quantum mechanics says something harsher. The photon did not have a simple classical story in the first place. It wasn't really a wave, or really a particle travelling one slit or both in a way your brain wants. The full quantum state evolves unitarily. Your choice of measurement basis at the end decides how that state gets projected into specific outcomes. In other words, the past you want to assign, it went through slit A, or it went through both slits as a wave, was never a definite, classical past. You aren't rewriting history. You're revealing which kind of question you decided to force on a non-classical system. Crucially, no accepted model based on these experiments lets you send a controllable message to your own past. You cannot flip a switch on Wednesday and have a friend on Monday decode a bit from changes in their earlier pattern. All the setups that actually work in labs keep causality intact at the level of signals and information. So entanglement and delayed choice wreck your intuition. They do not hand you a DeLorean. Where things start to look more dangerous is when you combine quantum mechanics with curved space-time. That's quantum field theory on curved backgrounds. Quantum fields living on a geometry shaped by gravity. Do that near a black hole and you get Hawking radiation. In the simplest picture, quantum fluctuations near the horizon produce pairs of particles, with one escaping to infinity and one falling in. To a distant observer, the black hole glows and slowly evaporates. You went from a clean classical object that only eats, never emits, to a quantum-corrected object that bleeds energy and shrinks. This leads straight into the black hole information paradox. If a black hole completely evaporates into what looks like thermal radiation, where did the detailed information about what fell in go? If it's really gone, that violates unitarity, a core rule of quantum mechanics. If it's somehow encoded in the radiation or stored on the horizon, then space-time and quantum theory are doing something far stranger than our current pictures show. Ideas like black hole complementarity say that different observers, someone falling in, someone watching from far away, get different but consistent stories about what happens. The horizon might act like a kind of membrane storing information. Then you get even harsher proposals like firewalls, where the smooth horizon dies, replaced by violent quantum structure. None of this gives you a usable time machine. You don't get a black hole you can use as a send message to past box. But it does scream a warning. Our current understanding of how quantum mechanics and gravity share causal structure is incomplete. The way information moves, the way cause and effect link up, the way horizons store or smear out data. All of that is less solid than our textbooks pretend. The big message is this. Whenever you push physics into regimes where both strong gravity and quantum effects matter, your clean story about this causes that in this order starts to look shaky. Not broken, but stretched. And time travel sits exactly in that danger zone. So now you're tempted to say, alright, maybe entanglement plus some clever protocol plus a black hole gives me a backdoor. Surely there is some loophole. This is where you have to be blunt. Quantum mechanics does not save your time machine fantasy. It gives you correlations that classical physics cannot match. It gives you non-local relationships between measurement outcomes. It gives you superpositions, interference, and delayed choices that smash any naive picture of particles as tiny billiard balls. But it does not give you clean, controllable, send a bit to the past operations. Every serious analysis, every no-signaling theorem, every test we've run says the same thing. Quantum weirdness lives on top of a causal structure that still respects light cones. You can entangle qubits across galaxies. You still can't send a meaningful message to last week. If time travel to the past exists anywhere in the real universe, it almost certainly lives in the geometry of space-time. Wormholes, closed timelike curves, exotic global structures, not in some cheap entanglement trick in a basement lab. And while quantum theory doesn't hand you a time machine, it does something almost worse. It hints that when we finally understand how space-time and quantum fields fit together in full quantum gravity, our current idea of time might not survive intact. That means every argument we make today about what is or isn't possible is built on a concept that might itself be an approximation. Before going that deep though, pull back. Look at the universe as a whole. There is a bigger clock ticking over all of this. Cosmic expansion, the age of the universe, the fact that when you look far enough away, you are literally seeing back in time. On the largest scales, the universe is already doing a slow-motion one-way time experiment we're all trapped inside. And that raises the next question. If the cosmos itself is a clock, with an age, a direction, and hard horizons beyond which you can never send a signal, how does that giant structure help or kill any hope of real-time travel? The universe has a birth certificate. It is not vague. It is not poetic. It is a number written into the radiation between galaxies, about 13.8 billion years. That is not someone guessing. That comes from brutal, precise measurements of the cosmic microwave background and the way galaxies cluster on huge scales. Missions like Planck map tiny temperature fluctuations in that background glow, feed them into the equations, and out comes an age. The result locks into other data, the way the universe expands, the way light from distant supernovae dims. All of it points to the same thing. The universe has been evolving for about 13.8 billion years since the hot, dense, early state we call the Big Bang. So therefore it is a cosmic stopwatch running. You're not just somewhen, you're sitting at about 13.8 billion years on that global timeline. Stars formed before you, stars will form after you. On large scales, cosmology gives you a hard number for how long this process has been going. Now look at what your telescopes actually do. When you point a big telescope at a galaxy 10 billion light years away, you're not seeing that galaxy as it is now. You're seeing it as it was 10 billion years ago. The light has been travelling through expanding space for that long just to reach your detector. Every extra light year of distance is one more year of look-back time. That means every clear night is full of ghosts. Nearby stars are delayed by years. Distant galaxies are delayed by billions of years. The cosmic microwave background is delayed by almost the full age of the universe. That's the afterglow from about 380,000 years after the Big Bang, still arriving today. You're always looking into the past, never at the present, never at the future. Say it in the hardest way. We already do time travel in one direction. We observe the past constantly. We just cannot walk into it. Light speed and cosmic distances turn telescopes into one-way time machines. They let you read old pages of the universe's history, but they never let you step through the paper. That's the first big constraint. No matter what exotic trick you imagine, you're operating inside a universe where information takes time to move and the sky itself is a delayed broadcast. Now, layer on the expansion of the universe. Space is not static. On the largest scales, galaxies are rushing away from each other as new space stretches in between. This is not galaxies flying through space like bullets. It is space itself expanding, carrying them apart. Far enough away that recession speed crosses a critical line. From our point of view, some regions are receding faster than light. That's allowed in general relativity because it's not motion through space, it's space itself stretching. But the effect on what you can reach is brutal. Those regions define a cosmic event horizon. Any signal we send now, light, radio, a probe, will never catch up to them. The expansion outruns it. Those parts of the universe are permanently disconnected from us in terms of future communication. We can maybe see some of their ancient light if it left them long enough ago, but there is a cut-off. Beyond that horizon, those worlds are forever unreachable, no matter how far into the future we wait. This means a lot of time travel fantasies are dead on arrival. Any scheme that assumes you can roam the entire universe, visit any galaxy given enough time, loop around and come back from the other side, is ignoring a basic fact. There are regions of space-time that are causally separated from you forever. They might as well be in another universe as far as your signals are concerned. Forward. Time travel by speed or gravity still works, but you do it inside a shrinking accessible bubble. As dark energy drives accelerated expansion, more and more distant galaxies slide over that horizon. The longer you wait, the less of the universe you can ever touch. Your future light cone shrinks in terms of what it can interact with, even as time rolls on. So does this giant expanding universe help or hurt the dream of real-time travel? On paper, general relativity lets you design wild cosmological models, bouncing universes that collapse and re-expand, universes with tunnels connecting distant regions, universes with different topologies that wrap around on themselves. You can put wormholes into cosmological backgrounds. You can imagine big crunch/big bang cycles where time might behave strangely at the transition. But when you look at the data, our universe is not choosing those exotic shapes. The model that fits observations best is boring in exactly the way that Hertz crazy time tricks. LCDM. Lambda cold dark matter. A universe that is, on large scales, homogeneous and isotropic, looks roughly the same in every direction and place, expanding in a smooth way, with dark energy, lambda, driving accelerated expansion. There are no signs of global rotation like Gödel's universe. No clear signatures of large wormholes warping the sky. The cosmic microwave background is uniform to 1 part in 100,000, with tiny fluctuations that match simple inflation plus quantum noise. The expansion rate, the way structures form, the way lenses bend light, all line up with a calm, predictable space-time background, not a violently twisted playground. That calmness is bad news for easy, naturally occurring time machines. If wormholes exist, they are not obvious features of the large-scale universe. If closed timelike curves exist, they are not screaming at us from the sky. Cosmic expansion gives you horizons and redshifts, not handy loops back into your own timeline. So cosmology, as far as we can see, does two things at once. It gives you a clear age and a clear arrow. The universe is older now than it was, structures have formed and evolved, and light from earlier times is still in transit. And slams the door on the idea that the universe itself is secretly littered with built-in shortcuts to the past. That pushes you into a harsher picture. On small scales, relativity bends time. On huge scales, cosmology locks in an age, a direction, and hard boundaries and what you can ever touch. The universe behaves like a giant clock that only moves forward, with parts of the dial drifting beyond your reach forever. So the next logical step is this. If the universe is expanding, aging, and building structure in one direction, and if entropy keeps climbing, is that what really nails down the arrow of time you feel in your bones? And if that arrow is as fundamental as it looks, does it quietly kill the idea of ever truly reversing anything, no matter how clever your space-time geometry is? You can reverse almost every microscopic equation in physics and it still works, but your coffee never unspills, your glass never unchatters, and you never wake up remembering tomorrow. That mismatch is the arrow of time hitting you in the face. At the level of fundamental laws, most of physics doesn't care about direction. Swap t for minus t in the equations of Newtonian mechanics or quantum mechanics, and they still describe valid motion. If you filmed two particles colliding and played the video backward, the reversed motion would still obey the same rules, no problem. But when you zoom out to real life, a brutal asymmetry appears. Entropy goes up. Entropy is a measure of how many microscopic configurations correspond to what you call the same macroscopic state. There are more ways for things to be messy than to be ordered, more ways for a gas to be spread out than crammed in a corner. More ways for your room to be a disaster than neatly arranged. So you see one direction favoured. Eggs fall, hit the floor, and splatter into a million pieces. The reverse, shards leaping up and knitting into a perfect egg, is not. Impossible in the strictest mathematical sense, but the odds are so ridiculously tiny that you will never see it once in the entire lifetime of the universe. Smoke spreads out into a room instead of clustering back into the corner. Ice melts in warm water. It doesn't spontaneously reappear fully formed. Your memory fits this pattern. You store records of low entropy configurations evolving into higher entropy ones. That bias gives you a sense of past and future. The laws don't force that direction. The statistics do. Entropy is the universe's one-way dial. So where did this dial get set in the first place? Why isn't everything already maximally scrambled? Cosmology's answer is harsh. The universe started in a very special state. The early universe, just after the Big Bang, was hot and dense, but in a specific, smooth, low-entropy configuration, especially in the gravitational sense. Matter and radiation were spread out almost uniformly. Tiny fluctuations were there, but overall, it was shockingly ordered compared to what gravity could have done. From that low-entropy beginning, the universe had room to run downhill in entropy. Gravity clumped matter into stars and galaxies. Nuclear fusion lit those stars. Planets formed. Heat flowed from hot to cold, from dense to diffuse. Chemical gradients appeared. Biology emerged to ride those gradients. Every irreversible process you see, friction, mixing, decay, rides on the fact that there are vastly more high-entropy possibilities than low-entropy ones, and the universe started near the low end. The direction of the arrow of time is set by that boundary condition, a low-entropy Big Bang evolving into higher-entropy everything. Without that asymmetry at the beginning, your sense of time having a direction would collapse, so the natural question is, could you flip the arrow somewhere, even locally? Could you carve out a lab, a ship, a region of space where the arrow of time runs backward? In principle, the microscopic laws allow entropy to go down in small systems for short periods. These are fluctuations. Given enough random motion, sometimes particles will, by chance, arrange into a more ordered configuration. It can happen, it does happen, in tiny ways, like brief small heat flow the wrong way on microscopic scales. But the probabilities are merciless. The bigger the system and the bigger the entropy drop you demand, the more absurdly unlikely it becomes. To get a whole room of air to spontaneously collect into one corner is effectively impossible. To get a human brain's worth of matter to reverse all its microscopic degrees of freedom and run cognition backward is beyond absurd. To truly reverse the arrow of time in a macroscopic region, you would need godlike control over every single degree of freedom in that region. Every molecule, every photon, every interaction. You'd have to engineer a precise conspiracy of positions and velocities on a scale that makes engineering a star look easy. That's not just difficult, it's outside any sane definition of feasible. So entropy gives you a one-way statistical arrow. It says typical histories go from low entropy to high entropy. Rare histories go the other way, but they are so outrageously rare that you can throw them away for any practical talk about reality. Now, tie this back to time travel. Everything we talked about with relativity, time dilation on rockets, gravitational time distortions near black holes, wormholes, closed timelike curves, that's about geometry, where you are in space-time, which path your world line takes. If the geometry is wild enough, you might find a path that re-enters its own past region. That's a geometric possibility. The arrow of time is about statistics. Given a path through space-time, what kind of microscopic evolution is overwhelmingly likely versus effectively impossible? That arrow will almost always line up with increasing entropy, no matter how bent the geometry is. So imagine, in the most generous way, that you find a geometric path that brings you back into a region of space-time corresponding to your past. Unless you also somehow reverse the entropy gradient, you're not going to see the world run backward like a rewound video. You will still experience processes going from lower to higher entropy along your own world line. You will still remember earlier, but not later. You will still break eggs, not unbreak them. That doesn't absolutely kill time travel, but it does crush the simplest naive fantasy. Just rewind the universe and do it over. Even with a perfect space-time loop, you're still chained to the arrow set by that low entropy beginning. To actually undo history in any meaningful sense, you'd have to overturn both geometry and statistics, so now you're trapped in a much narrower corridor. Relativity might let you loop paths. Entropy tells you that even on those loops, you still live forward. That tension is exactly where the famous time travel paradoxes live, trying to change a past that statistically and causally may already be locked into consistency, and that pushes us straight into the ugliest part of the story. If you ever do manage to get back into your own past light cone, do you tear logic apart with paradoxes, grandfather bootstrap information from nowhere? Or does the universe quietly force you into a timeline where you can't break anything at all? Time travel isn't scary because of equations, it's scary because of logic. The moment you say I can go back, you slam straight into questions that don't care about your feelings. Can you rewrite facts? Can you erase yourself? Can you create something from nothing just by looping it through time? Start with the grandfather paradox. You step into your time machine, go back to a time before your parents were conceived and kill your grandfather. Cold. No grandfather, no parent, no you. But if you never exist, you never step into the time machine. If you never step into the time machine, your grandfather doesn't die. Then you exist again, then you go back, then you kill him again. The story doesn't settle. It oscillates between you exist and you don't, with no stable answer. That's not just Zen, that's a logical contradiction. A world where both you existed to go back and you never existed have to be true at the same time. Then the bootstrap paradox. You go back with a book of advanced physics. You hand it to your younger self or to some scientist in the past. That scientist publishes it. The knowledge spreads. Decades later, you grow up, read the same book, and use it to build the time machine, and then you go back and deliver the book. Where did the information actually come from? There is no origin. It just lives on a loop in time. The knowledge exists, but it was never created by anyone. Same for objects. A time traveler hands a ring to their younger self. The younger self keeps it for decades, then one day hands it back to their older self to complete the loop. The ring never gets manufactured in ordinary time, it just circulates. Matter and information with no causal source. Then information from nowhere in a more abstract form. You receive a message from the future with tomorrow's lottery numbers. You play, and then later you send that same message back. The numbers are correct, but no one ever actually computed them in a normal causal way. They're just there because the loop says so. These are stress tests. They're not meant to show how time travel would normally work. They're meant to smash into it and see if the idea breaks. If you allow free arbitrary changes to the past, you end up with contradictions or causally originless loops. That's not just weird, that's unstable logic. So, what can you do? One answer is, the universe simply does not allow you to break it. That's the spirit of Novikov's self-consistency principle. It says, if closed timelike curves exist, if you can travel into your own past, then the only histories allowed are the ones that are globally self-consistent. You can be part of the past, you can interact with it, but you can only do things that were always going to happen. You go back and try to kill your grandfather. You aim, you fire, and the gun jams, or you slip, or you hit someone else, or you decide at the last second not to do it. Every attempt to change the key event fails in some way, not because you're cursed, but because in the actual history of the universe, your grandfather already survived. Your time travel was part of that story all along. In a Novikov world, the bootstrap paradox isn't a bug, it's just how things are. The book with the advanced physics has no normal causal origin, but the loop itself is the origin. The information exists because the entire space-time history is one fixed, self-consistent object. You don't get to ask who wrote it first in the usual way, because there is no first. There's just the loop. This view is brutal. It crushes the fantasy of go back and change things. You can go back and cause things, but only the things that were already true. Free will gets squeezed. You feel like you're choosing, but in reality, only the choices that maintain consistency actually occur. Everything else has probability 0. Some people hate that, so they reach for another escape. Maybe when you mess with the past, you don't rewrite your own timeline, you drop into another one. That's the many-world style answer. In quantum mechanics, the many-worlds interpretation says the wave function of the universe doesn't collapse, it branches. Every quantum event with multiple outcomes creates new branches where each possible result happens in a different world. They all exist in the global wave function. Now, bolt time travel onto that. You step into a machine, go back and do something different. Maybe you kill your grandfather. In a many-worlds picture, you haven't created a contradiction. You've moved into, or created, a branch where you, the time traveller who arrived and killed him, was always part of that history. Your original branch, where your grandfather lived and you were born, still exists and keeps going. The branch where you erased your own family tree exists alongside it. No paradox, because no single timeline has both grandfather lives and grandfather dies. They're separated into different branches. Likewise, the bootstrap paradox morphs. The book of physics or the ring might still live on a loop, but it loops within a branch structure that is part of a bigger multiverse. You're no longer demanding that everything fit into one self-contained history. The cost is heavy. You've replaced a single universe with an enormous branching structure. Every change you make doesn't overwrite anything. It just positions you in a different slice of the wave function. You aren't rewriting your own past. You're becoming the version of you that appears in a different history that always included your interference. So where does actual physics land between these options? Our tested theories don't commit. General relativity says some spacetimes allow loops in time. Quantum mechanics in many formulations suggests branching, or at least a more subtle structure of history than a single classical story. Semi-classical calculations near would-be time machines hint that quantum effects may blow things up before paradoxes appear. But we do not have a final unified theory of quantum gravity that says, once and for all, this is how time and causality behave in every extreme situation. What we do know is this. General relativity admits closed timelike curves in some solutions. That's not in dispute. No experiment has ever shown violations of causality. No verified messages from the future. No lab setup where effects consistently show up before causes. No actual paradox events. Precision tests of relativity and quantum theory always come out boring in one key way. They respect causal order when you look at signals and information. Most working physicists, whether they talk about it or not, strongly suspect that something, maybe Hawking-style chronology protection, maybe deeper consistency rules in quantum gravity, maybe a many-world structure that hides paradoxes in branching, saves causality. But right now, that's not a theorem. It's a bet. The war isn't over. Time travel to the past is not cleanly banned by the math we have, but it is also not supported by anything we've ever seen happen. The equations flirt with loops and paradoxes. Reality keeps them at arm's length. And, while the pure theory people argue about consistency and multiverses, the experimental side has been doing something else, trying to break relativity in the lab for real, looking for faster-than-light particles, strange signals, or any crack in the rules. Every time someone thought they'd found one, the universe answered with a harsh correction. In 2011, for a short, insane moment, it looked like the universe had blinked. The Opera experiment in Italy sent neutrinos from CERN in Switzerland to Gran Sasso, about 730 kilometers through rock. They measured departure times, arrival times, distances, and when they crunched the numbers, the neutrinos seemed to be showing up about 60 nanoseconds too early. That implied a speed slightly faster than light. If that were real, it would smash one of the core pillars of relativity. Faster than light travel means you can, in some frames, send signals into the past. That's not just weird, that's a direct shot at causality. For a few months, headlines screamed faster than light neutrinos, and Einstein was wrong. People started asking, does this mean time travel is real? Is this the crack? The experimenters were careful. They didn't immediately claim a revolution. They said, we see this anomaly. We've checked everything we can think of. Please, world, help us find the error. Other groups prepared to repeat the measurement. Theoretical papers appeared overnight with wild models trying to shove faster-than-light neutrinos into some kind of consistent framework. Then reality did what it always does. It killed the drama with a stupid detail. The culprit turned out to be a loose fibre optic cable in the timing system and an issue with an oscillator used for GPS synchronization. The timestamps were slightly off. Once they fixed the hardware and recalibrated, the neutrino's speed dropped back down right where relativity said it should be. Extremely close to, but not exceeding, the speed of light. No violation, no causality break, no time travel neutrinos, just a bad connection. That episode was a perfect example of how this game actually plays out. The smallest hint of faster than light anything sends physics into high alert, because it would mean our entire structure of space-time and cause and effect is incomplete in a catastrophic way, but every time we chase one of those hints hard enough, it collapses into noise, miscalibration, or misunderstood systematics. Meanwhile, the experiments that actually work get more and more precise, and they all point in the same direction. Relativity is stubborn. Atomic clocks keep getting better. We put them on planes, rockets, satellites. We stack them vertically in towers, with one a few tens of centimeters above the other. We let them tick, then compare. Every time the same pattern appears. Clocks in motion experience special relativistic time dilation. Moving clocks run slow relative to stationary clocks. Clocks deeper in a gravitational field experience general relativistic time dilation. Lower clocks run slow relative to higher ones. Combine the two effects and you get exactly what Einstein's equations predict, to absurd levels of precision. Experiments like Hafele-Keating's airplane clocks were just the start. Modern optical lattice clocks are so precise they can see the difference in tick rate between two clocks separated by less than a meter of height in Earth's gravity. You move a clock up a staircase and the theory says it should tick faster. The clock agrees. You fly one around the world and bring it home. It disagrees with the stay-at-home clock by exactly the amount predicted. Every one of these experiments is a chance for reality to say, surprise, relativity fails here. Here's your opening for a time machine. Instead, what we get is the opposite. The more we push, the more the boring, rigid structure of relativity gets confirmed. The math that lets you dream up wormholes and warp time also. Locks in hard constraints, no cheap shortcuts, no obvious loopholes. On the quantum side, labs have been building fake spacetimes, analog systems that simulate key features of curved geometry without actually bending cosmic scale spacetime. You can create analog black holes in fluids, where sound waves or surface waves experience horizons. You can engineer condensed matter systems where excitations move as if they're living in a spacetime with an effective metric mimicking aspects of gravity. In these setups, people have seen phenomena that look like Hawking radiation analogues. Thermal-like emission from horizons, not in real gravity, but in these controlled systems. These are toy universes. They let you probe the logic of horizons, information flow and causal structure in ways you can't do with actual black holes light years away. There are powerful tools for testing ideas about how quantum fields behave near horizons, how information might leak out, and whether some weird time effects could show up. But they do not give you a time machine. You don't get a lab where you can send a signal to yesterday. You get insight. You get constraints. You get more reasons to believe that even in extreme conditions, nature is hostile to any clear, usable causality violation. So pull these threads together. Every time someone claims we've broken relativity, reality responds with something embarrassingly mundane. A bad cable, a misaligned mirror, an unaccounted for delay, a calibration bug. The big flashy claims evaporate under scrutiny. The quiet, careful experiments keep piling up evidence that space-time and light speed are doing exactly what the textbooks say. That's not the universe being boring. That's the universe telling you that if there is any real way to go beyond forward time dilation, any way to loop back, any way to send information into your own past, it is not sitting in obvious places. It's not hiding in neutrino timing glitches. It's not hiding in a simple clock trick. It's not waiting to be discovered by someone who forgot to tighten a connector. If time travel beyond go fast, go deep in gravity, come back in the future exists, it's buried deep under layers of consistency, quantum gravity, and extreme conditions. You will not unlock it with a slightly weird measurement in a press conference. You will only even touch it by understanding the structure of space-time and energy at a level we simply do not have yet. And that's exactly why the theoretical stuff people write off as sci-fi, warp drives, negative energy, space-time engineering is so dangerous. Because if any of that turns out to be physically real, it doesn't just mean go to another star faster. It means you might accidentally build the one thing the universe has been resisting this whole time, a machine that can weaponize causality itself. Alcubierre's idea hits like a glitch in the rules. You don't move faster than light through spacetime, you drag spacetime itself. His solution to Einstein's equations describes a warp bubble, where space is compressed in front of your ship and expanded behind it. Inside the bubble, you sit still. Locally, every measurement you make respects the speed of light, but relative to distant observers, the bubble can move effectively faster than light across the universe. From your point of view, you're just coasting in a pocket of flat space-time, no crazy forces, no engines roaring at relativistic speeds. The weirdness is all outside in the metric, the geometry of space-time. The front edge of the bubble is where space shrinks. The back edge is where space stretches. Stitch this together, right? And your position in the larger universe can change faster than any photon travelling in normal space. On paper, this dodges the usual "you need infinite energy to reach light speed" problem. You never accelerate the ship itself to see. You keep your local velocity subluminal and let the metric do the dirty work. General relativity doesn't scream no at this. It shrugs and says, if you feed me the right stress energy, I'll give you that geometry. The catch is what that stress energy has to look like. To generate and maintain an Alcubierre warp bubble, you need regions of space-time with negative energy density relative to some observers. Not just low energy, negative. The stress energy tensor that supports the warp bubble violates the standard energy conditions that ordinary matter respects. Early calculations were brutal. They said you'd need negative energy comparable to the mass energy of Jupiter or more, arranged in a specific shell around your ship. That's not big project territory. That's congratulations, you just tried to reorder cosmic bookkeeping territory. Later refinements played with the shape of the bubble, the wall thicknesses, clever tweaks to the metric. They chipped away at the energy requirements, reducing them from planet size towards still ridiculous. But even the optimistic versions demand absurd amounts of exotic negative energy density, far beyond anything our physics knows how to produce and shape on macroscopic scales. We do know about tiny negative energy phenomena. The Casimir effect is the standard example. Put two conducting plates very close together in a vacuum, and quantum field modes between them get restricted. The result is an attractive force you can interpret as a region of lower than normal vacuum energy between the plates. You can call that an effective negative energy density relative to the outside. But that is microscopic, fragile, and strictly constrained by quantum inequalities. It's not a slab of warp fuel you can pour into a ring around your starship. It's a delicate, tiny effect that appears in special setups and disappears as soon as you loosen the geometry. Turning that into drive your ship to Andromeda in a weak hardware is not a small step. It's a leap into fantasy with no bridge. So, Alcubierre gave us a geometry that does exactly what sci-fi always wanted. Effective superluminal travel without locally breaking C. Physics responded, sure, if you can feed me monstrous amounts of negative energy that nothing in your universe seems able to provide. Now comes the darker part. Suppose, for the sake of argument, that some advanced civilization really can do this. Suppose they somehow solve the negative energy problem and can generate stable warp bubbles that move faster than light relative to distant observers. What happens to time travel? Relativity already tells you the answer. If you allow superluminal travel of any kind, you can usually arrange those paths so that, from some reference frames, they form closed timelike curves. In plain terms, you stitch together two or more warp trips and normal motion in such a way that you leave one place, take a warp path, come back along another path, and end up at an event that lies in your own past light cone. The situation is like the old tachyon anti-telephone paradox. If you can send a signal faster than light, then in some inertial frames that signal goes backward in time. Combine two such signals and you can send information into your own past. Replace tachyon signal with warp bubble carrying a ship, and the same geometry games apply. Once you have a tool that moves you around space-time faster than light relative to the background, you can abuse it into a time machine. So any civilization that builds working warp drives doesn't just go to distant stars quickly, they get access to closed time-like curves if they choose to arrange their flight paths that way. They get the ability, in principle, to build causality violations into their transportation network. That's the dark side. Warp tech and time machines are not separate topics. In a relativistic universe, they're linked. Superluminal geometry almost automatically drags time loops in behind it. Now, slam back to where we actually are. Right now, warp drives and large-scale negative energy structures are sitting in the same bucket as traversable wormholes. Beautiful equations, zero hardware. We have metrics that do what we want on paper. We have no known way to supply the stress energy they demand, no. Lab evidence that macroscopic negative energy beyond tiny quantum effects is available. And serious theoretical reasons, quantum inequalities, stability issues. To suspect the universe won't let you scale those effects up arbitrarily. From a sober engineering standpoint, Alcubierre drives are science fiction. There is no design path from Casimir plates to a warp ring around a ship. No material, no generator, no testbed. But for time travel, the key connection is this. If you could do it, if you could somehow stabilize a warp bubble and push it superluminal, then time travel to the past would leap from probably impossible to dangerously plausible. The same relativity that protects the speed of light also tells you that any genuine workaround is almost automatically a weapon against causality. So the universe seems to be playing defense. It lets us write down the metrics. It tempts us with neat solutions. Then it buries the implementation under requirements that look designed to be unreachable. Which leaves one last angle to explore. Maybe you don't move yourself through time at all. Maybe you only move information by reading the deep past written into light, rocks, and waves, while never getting a chance to write back. If you can't edit history, how far can you go just by reading it with more and more brutal precision? You already watch ancient history live, you just call it astronomy. When a big telescope locks onto a faint smear of light billions of light years away, it's not seeing that galaxy now. It's seeing it when the universe was young and brutal and Earth didn't even exist. The photons hitting the detector left their source when everything here was still just future potential. Some of the galaxies we see with our biggest telescopes are from a time when the universe was less than 1 billion years old. Massive stars were forming, exploding, seeding space with heavy elements for the first time. We don't guess this. We see in the spectra and shapes of those galaxies. That light has been in flight for the billions of years and only now lands in your instruments. So every deep field image is a layered time map. Closer galaxies, a few tens or hundreds of millions of years old as they were. Farther ones, billions of years back. The cosmic microwave background, a snapshot from when the universe was only about 380,000 years old. Your eyes, through a telescope, are sampling different slices of the past stacked in distance. Call it what it is, one-way observational time travel. You're not going there, but the light is coming from there, carrying information about conditions that no longer exist. You observe the past every clear night. You simply have zero power to step into it. On Earth, the same principle is buried under your feet. Rocks are memory devices. They don't just sit there, they recall. Radiometric dating uses unstable isotopes, radioactive variants of elements, as clocks. Take uranium-238, for example. It decays into lead-206 with a known half-life of about 4.5 billion years. Measure how much uranium and how much lead there is in a crystal that locked those atoms in place when it formed. Use the decay law. You get an age. Do the same with different isotope pairs, uranium-lead, potassium-argon, rubidium-strontium, and you cross-check. Those ratios are not opinions. They are the integrated result of nuclear decay running without pause for hundreds of millions or billions of years. A zircon crystal doesn't care about your calendar. It just sits there, its isotopes quietly stepping down their decay chains, ticking off deep time. Then add geological stratigraphy. Layers of sediment stack over each other. The lower layers are older, the upper ones younger, unless something violent has scrambled the stack. Inside those layers, fossils, ash falls from ancient eruptions, traces of impact events, chemical signatures of climate shifts. You read that vertical structure like a timeline. Here, a mass extinction. Here, a slow shift in ocean chemistry. Here, the first appearance of a certain shell type. Each layer is a page of the planet's history, written in rock, isotope ratios, and dead things. So between telescopes and geology, you already have two massive independent systems that let you read billions of years of history. One cosmic, one local. Neither lets you touch what you're seeing. Both are pure information time travel. Now, add the newest tool, gravitational waves. These are not light. They are literal ripples in space-time emitted by accelerating masses, especially extreme ones like black holes and neutron stars. When LIGO detected the first clear signal, GW150914, it was picking up a merger of two black holes about 1.3 billion light-years away. Those waves took about 1.3 billion years to reach Earth. For all that time, they propagated through the expanding universe, stretching and squeezing space as they went, untouched by gas and dust that absorb light. When they passed through LIGO's detectors, they changed the length of the interferometer arms by less than 1,000th of the width of a proton, and we still saw them. Listening to that signal is listening to a violent event that happened before complex life appeared on land here. Two black holes, each tens of solar masses, spiraled together and merged, converting several suns' worth of mass into pure gravitational wave energy in a fraction of a second. That final chirp in the LIGO data is the last moment of that collision, arriving now long after the actual black holes have settled into a single remnant out there. This is gravitational wave archaeology. Every detection, GU150914, GU170817, with neutron stars, all of them, is a time-stamped message from deep past events. You're not seeing them as they are now. You're seeing them as they were, delayed by the travel time of space-time ripples themselves. So across all these channels, light, particles, gravitational waves, rocks, the universe is constantly dumping history at your feet. Photons from early galaxies, microwaves from the infant cosmos, isotopes counting down in ancient minerals. Space-time ripples from dead stars. You're drowning in data from the past. Here's the crucial thing for time travel. This is real. This is not tentative or speculative. You're already reading the timeline of the universe across absurd spans. You can reconstruct star formation histories, galaxy growth, chemical enrichment, planetary ages, extinction cycles, black hole mergers. You can pin dates on events that happened billions of years before your species existed. But everything you do is read-only. You can't reach into that galaxy 10 billion years ago and tweak it. You can't go back to the moment before those black holes merged and nudge their orbits. You can't whisper into the rocks to stop an asteroid 66 million years ago. The information flows one way, from past events to present detectors. Time travel as editing history is fundamentally different from time travel as reading it. To edit, you'd have to inject influence backward along those causal chains. You would have to send something, matter, energy, reliable information, into regions that, from your standpoint, are fixed and closed. Everything we know says you can't. So you're stuck in a strange position. You live in a universe that hands you an insane amount of access to its own memory. It lets you see almost all the way back to the beginning. It lets you date rocks, decode fossils, and listen to ancient collisions in space-time. It gives you the script, and then it nails shut the door to rewriting any of it. That's why when you finally ask the big question, is time travel actually possible in this universe? You have to split the answer. There's the part we already do every day without noticing, and there's the part the universe seems to fight with everything it has. Here's the blunt verdict. Time travel is not some distant sci-fi fantasy. Parts of it are already running in the background of your life, enforced by the laws of physics whether you care or not. Start with the piece that's not up for debate. Forward time travel is absolutely real. We've seen it in motion time dilation. Clocks on planes, rockets and satellites tick at different rates. From clocks on the ground, we've flown atomic clocks around the Earth and watched them come back out of sync exactly the way Einstein's equations demand. We've parked clocks on the ISS and measured a tiny age gap for astronauts who spend months moving at orbital speeds. We've seen it in gravitational time dilation. Clocks at the bottom of a tower runs slower than clocks at the top. Clocks deep in Earth's gravity age a bit less than clocks high above. GPS satellites orbiting higher up in weaker gravity tick faster than ground clocks and have to be deliberately offset or your navigation would drift by kilometers per day. Do it with particles and the effect becomes brutal. Muons in accelerators live 10, 100 times longer when they're pushed near light speed. Their decay clocks slow down relative to ours. That's not a theory. That's the calibration of every high-energy physics lab on the planet. All of that is just the small version. Scale it and you get human-level time jumps. Build a ship that cruises at 0.99 C and 20 years for you can line up with more than a century back on Earth. Drop into a safe orbit near a supermassive black hole, let time crawl for you while the universe races ahead outside, then climb back out. Same equations, same physics, just to insane conditions. So, going into the future faster than everyone else is possible in principle. No new physics required. Relativity has already signed off on that. The only obstacles are engineering, biology, and money. Now, the part everyone actually cares about, going backward time travel, round-trip time tourism, I left 2300 and came back to 2025. That sits in a net uncertain zone. On the chalkboard, general relativity absolutely allows structures that look like time machines. Closed timelike curves, wormholes with time-shifted mouths, warp bubbles bent into loops. You can draw spacetimes where you leave an event, follow a timelike path, and return to that same event's past. On the other hand, everything we know about matter, entropy, and quantum fields screams, "Don't you dare!" Traversable wormholes seem to require negative energy densities on the macroscopic scales. Warp drives demand exotic stress energy that nothing in nature has ever shown us. Attempts to form closed timelike curves from normal initial conditions often run into quantum blow-ups. Vacuum fluctuations diverging near the would-be time loop threatening to rip the geometry apart before a paradox can ever happen. Add in Hawking's chronology protection idea, and the message is clear. The math is permissive, but the universe might not be. The solutions exist in the space of equations, yet our actual universe gives us no hint that it ever realizes them in the wild. No wormholes, no warp bubbles, no lab-made closed timelike curves. Even with gravitational wave detectors listening to colliding black holes and telescopes mapping the early universe, we see exactly zero clear evidence of anything that behaves like a real-time machine. So, backward time travel is in the maybe but don't bet your life on it category allowed in some GR solutions, probably strangled by quantum effects, energy conditions or boundary conditions, totally unsupported by direct observation so far. Then there's the stuff that's basically dead. Using quantum entanglement to send messages into your own past? Every no signaling theorem and every experiment says no. You get spooky correlations, not controllable retro messages. Delayed choice and quantum eraser setups don't rewrite history. They just expose how wrong your classical picture of what really happened is. Trying to violate causality in clean lab experiments? Faster than light neutrinos? Each time someone announces a crack, it collapses into bad cables, miscalibrated clocks, or misunderstood noise. High-precision tests of relativity and quantum theory keep coming back with the same answer. Causal order is incredibly rigid. At the level of signals and information, the universe keeps cause before effect. So here's the split, stripped of romance. Definitely possible. Forward time travel, via motion, and gravity. Planes, satellites, ISS, particle beams, black holes, relativistic starships, all on the same theory. Maybe if the universe is nastier than we think, actual trips into your own past via wormholes, CTCS, warp geometries. The equations allow it, the matter content and quantum corrections seem to fight it, and reality has not shown us a single working example. Almost certainly impossible with what we know. Quantum texting your younger self, cheap lab-scale causality violations, or any scheme that pretends you can ignore light cones and still keep physics consistent. You end the story here, and you don't sugarcoat it. You already live in a universe where time bends, stretches, and disagrees with itself. We've flown clocks that come home younger, watched particles outrun their own deaths, and listened to space-time ring like a bell from black holes that merged before dinosaurs existed. Time travel isn't a question of if, it's a question of how much and how far. The future, we can absolutely visit it faster than everyone else. The past, for now the universe keeps that door locked. But every new wave we detect, every particle we time, is us quietly jiggling the handle. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.